We're now going to take the Gibbs formulation and show that in fact it leads us to perhaps one of the most famous equations from molecular thermodynamics. Okay, so let me remind you that the Gibbs formulation of statistical entropy could be written as follows, that the entropy is equal to minus Kb times the sum over all of the states of the system times their probabilities times their logs of their probabilities. Right? There was also an integration constant, and I'll add that to be formally correct, but we'll find out later from the third law how to deal with that particular aspect. I want to focus, though, on this part of the formulation of the entropy. All right, now what we're going to do is we're going to start by noting that, for example, if I have a quantity that looks like this, a times log x, that's just the same as log of x to the a. So I'm going to apply that to each of the terms in this sum so that I can actually write something, and I'll put it over here to the side just to give myself a little extra room, that actually is going to give me something that looks like this. So I'll have sum over j log of pj raised to the pj power. Now you may be wondering, am I crazy? Why would I ever want to do something like this? Isn't this making it more complicated? Is this going to make it harder to deal with? Well, I'm going to do something, I'm going to do another step that you might not like either, and that is I'm going to say, let's just write out this sum, what the various terms in this sum might look like. So we'd have minus kb, and now instead of having the summation sign, I'm going to write this as log of p1 raised to the p1 power plus log of p2 raised to the p2 power. And don't worry, I'm not going to write them all out, but you get the idea. We're going to have a bunch of terms that looks like this. But whenever I have things that look like log of a plus log of b, that's really just going to be equal to the log of the product of those things. So in other words, I'm going to have the log of the product of all of these things laying out here. So I'll have minus kb times the log, and now my log is going to be p1 to the p1 times p2 to the p2 times p3 to the p3 and so forth times dot dot dot. Now this doesn't look like I've made it look any better, does it? I mean, what on earth are we going to do with all of this? Well, here's where we're going to actually build in a little bit of an approximation, but it's due to if we're at a thermal equilibrium. Remember that one of the assumptions that we made in developing the most probable distribution that got us to the thermal equilibrium distribution was we said that we're going to have a total of W microstates, and all of them are equally probable. Well, if all of them are equally probable, that means that I can write P sub j is equal to 1 over W, okay, because I have a total of W microstates, so each one is going to be 1 over W probability, and it does not depend on j. So it's going to be the same for all of the microstates. So now I can substitute that in for each of these values here. Now I'm not going to do it for the values up here for a reason that you'll see in just a moment. But that means I can write this as this. I've got 1 over W raised to the P1 power times 1 over W raised to the P2 power times so forth. Now, whenever I have something like this, that's just going to be, whoops, and I forgot the log. That's not good. Okay, it's log of all of this stuff. So it's going to be minus kb times the log of 1 over W raised to the P1 plus P2 plus P3 plus so forth for all of the states in the system. Okay, but the sum of the probabilities of all the states in the system, P1 plus P2 plus P3 and so forth, is just equal to 1. That's the total probability. So in other words, I've got S is equal to minus kb log of 1 over W raised to the first power, so it's just log of 1 over W. Well, log of 1 over W is negative log of W, so I can have negative signs cancel. I will end up with this as my final result, and this is what I was referring to as one of the most famous equations of molecular thermodynamics. This is the Boltzmann formulation of the entropy, And it was recognized for its power even in his lifetime and after his death, because it's inscribed on his tombstone. And that's one of the pictures at the beginning of the lesson. All right, so what we've actually gotten out of all of this is, remember way back at the beginning of the previous video, we started with this formulation. This was the thing we used to define thermodynamic entropy. And we essentially showed that it was equivalent to the Gibbs formulation for the entropy, which we wrote like this. But now we've shown that the Gibbs formulation leads us to the Boltzmann formulation for the entropy. Oops, not minus, plus kb log of W. And what this is telling us is that all of these versions of the entropy are consistent with one another. So whether we use the thermodynamic value of the entropy or we use a statistical version for the entropy, we're talking about the same quantity in general. And I also want to point out especially that from Gibbs' result here, that we have this thing that relates the entropy directly to the number of microstates. So the thing that we were hypothesizing earlier about the connection between the growth of entropy and the growth of microstates is absolutely encapsulated in this equation. So now on, when we talk about entropy, you should think about it in terms of the availability of states to the molecule. Entropy is not something that drives an equation so much as the drive is furnished by the fact that it provides, it's leading you to a destination that has a much greater number of microstates to choose from. So it's really just a game of probabilities.